In episode 24, titled Network Virtual Interfaces, What vNICs Imply for Control and Visibility, we treat virtual interfaces as the attachment point for network controls because almost every modern cloud and virtualized network decision eventually lands on an interface boundary. A physical server once had a small number of physical ports, but virtual environments create interfaces in software, and that flexibility changes how you build trust zones, how you apply policy, and how you observe traffic. The exam uses this concept to test whether you understand where control actually happens, because you can design beautiful segmentation on paper and still fail if the interface attachments are wrong. Virtual interfaces also change visibility, because flow logs, security rules, and monitoring often attach to the interface rather than to the workload in the abstract. When you understand what a virtual network interface implies, you can reason about security groups, routing behavior, performance limits, and troubleshooting signals more quickly. The goal is to make the interface feel like a deliberate design object, not a background implementation detail. Before we continue, a quick note: this audio course is a companion to the CloudNetX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A virtual network interface, often shortened to vNIC, connects workloads to switches, routers, and security policies by acting as the workload's presence on a network segment. In a virtualized environment, the vNIC is what receives an address, what sends and receives frames, and what participates in the local forwarding domain in the same way a physical network card would. That means the vNIC is the point where a workload becomes reachable and where it can initiate connections, which is why it becomes a natural control point for segmentation and policy enforcement. The vNIC is also where the network's identity of the workload is expressed, such as the address it uses and the media access control information that local switching relies on. When a scenario question talks about attaching a workload to a subnet or applying security rules to an instance, it is often describing vNIC behavior, even if it never uses that term. This is also why changes to vNIC configuration can have immediate and dramatic effects, because you are changing the attachment point itself rather than tuning a higher layer setting. Understanding that the vNIC is the point of attachment helps you interpret exam answers that focus on interface-level policy. Multiple vNICs enable separation of management and data traffic, and this separation is a common design pattern because it reduces blast radius and makes control intent clearer. Management traffic includes administrative access, monitoring, backups, and replication control, while data traffic includes user-facing application flows and service-to-service flows that support the business workload. If both types of traffic share one interface and one subnet, a compromise or a misconfiguration can expose management paths and increase the risk that an attacker pivots from data plane access into control plane access. With separate vNICs, you can place management traffic in a restricted subnet with tighter policy and limited reachability, while keeping application traffic in a subnet designed for scale and performance. This also improves troubleshooting because you can reason about which interface should carry which flow, and anomalous traffic stands out more clearly. In exam scenarios, when you see language about separating administrative access or reducing blast radius, multiple vNICs are often the implied mechanism. The key is that separate interfaces allow different control rules and different routing paths, which is difficult to achieve cleanly with one interface alone. Media access control addressing matters in virtual environments because the vNIC participates in Layer 2 behavior, and duplicates can create confusing reachability problems that look like random failures. A media access control address is used for local delivery, and switching relies on it to map where a device is connected, even in virtual switching environments. If two interfaces share the same media access control address, a switch can learn the address on one port and then learn it on another, causing traffic to be delivered inconsistently as the mapping flaps. The symptom can be intermittent reachability, sessions that break unexpectedly, or traffic that appears to go to the wrong destination, and these issues can be very difficult to diagnose if you are not considering the Layer 2 identity. Duplicate media access control problems can arise from cloning, snapshotting, template misconfiguration, or errors in automation, which is why they are relevant in cloud and virtualization contexts. In exam scenarios, when the prompt describes intermittent connectivity after cloning or rapid provisioning, media access control duplication is a plausible hidden cause. The important lesson is that virtual does not mean immune to Layer 2 identity rules, and duplicates can break networks just as effectively as in physical environments. A disciplined design practice is to build subnets per vNIC so purpose is clear, because clarity reduces both security mistakes and operational drift. When each interface has a defined purpose, the subnet it attaches to should reflect that purpose in its address plan, its routing, and its policy. If an interface is for management, its subnet should have restricted reachability, strong inspection, and clear ownership, while an interface for application data should be placed in a subnet aligned with the service's traffic patterns and scaling needs. This practice also improves log interpretation because source addresses and subnets become meaningful indicators of intent, making it easier to spot anomalous flows. Subnet per purpose thinking also reduces the temptation to create ad hoc allow rules because the network structure itself expresses what should be able to talk to what. In exam terms, answers that attach interfaces to clearly defined subnets tend to align with best answer logic because they reduce ambiguity and strengthen segmentation. The design point is not that every interface needs its own unique subnet in every case, but that the subnet should reflect the interface's trust zone and function. Security group attachment is a major control implication because stateful rules often apply at the vNIC, meaning the interface is where allow and deny logic is enforced for inbound and outbound flows. When security groups attach to the vNIC, they become part of the workload's network identity, controlling what traffic is permitted to reach the workload and what traffic the workload can initiate. Stateful behavior means that return traffic for an allowed session is typically permitted automatically, which can simplify rules but also requires you to think carefully about what sessions you allow to begin. Applying rules at the vNIC level is powerful because it follows the workload even if it moves within the environment, and it allows segmentation without relying exclusively on centralized firewalls. It also means that misconfiguring the security group on the wrong vNIC can either block critical traffic or expose sensitive paths, which is why interface association matters. In exam scenarios, when the prompt mentions security groups, stateful rules, or instance-level access controls, vNIC attachment is the control plane location you should picture. The best answers usually reflect that policy should be applied as close to the workload as possible while preserving operational clarity. Performance is another implication because vNIC offload features and queue depth can affect throughput directly, and virtual interfaces are not just logical labels, they are tied to resources. Offload features can reduce CPU overhead by handling certain network processing tasks in a more efficient way, and when they are enabled and supported properly, they can improve throughput and reduce latency under load. Queue depth and interface buffering affect how many packets can be handled during bursts and how well the workload can keep up with incoming and outgoing traffic without dropping. In virtual environments, these settings interact with host capacity and with the hypervisor or cloud platform implementation, which means performance issues can sometimes be caused by interface level limits rather than by application inefficiency. Exam scenarios sometimes hint at this by describing a workload that cannot achieve expected throughput despite sufficient bandwidth, or by describing performance changes after modifying interface types or settings. The key is that interface choice can be a throughput decision, not only a segmentation decision. When you treat vNICs as resources, you become more likely to choose answers that match performance constraints realistically. A practical example is attaching a second vNIC for backup replication traffic, because it shows how multiple interfaces can reduce risk and improve predictability. Backup replication often generates heavy traffic and can be sensitive to latency and loss, and it should not compete directly with user-facing application traffic if you want stable performance. By placing replication on a separate vNIC in a separate subnet, you can route it along an intended path, apply specific security rules, and monitor it as a distinct flow category. This also reduces blast radius, because compromise of application traffic does not automatically grant access to the backup network, and vice versa, assuming policy is correctly enforced. Operationally, it makes troubleshooting easier because spikes in replication traffic are visible on the replication interface rather than being mixed into all traffic metrics. In exam scenarios, when the prompt includes replication traffic, backup network, or separate management plane, a second vNIC is a plausible design answer because it aligns separation with purpose. The best choice usually includes both the interface separation and the policy separation that follows it. A common pitfall is misassigning a vNIC to the wrong subnet because that breaks access immediately by placing the workload into an unintended trust zone or routing domain. If an application interface is attached to a management subnet, users may lose access because routing and security policies do not permit the expected inbound flows. If a management interface is attached to an application subnet, administrative access may become exposed or may fail because the management path now traverses controls not designed for it. Misassignment can also create subtle issues when the workload has multiple interfaces and uses the wrong one as a default path, causing traffic to exit through a subnet that does not allow return paths or that enforces different inspection. In exam scenarios, this can show up as "it worked before a change," or "only some flows fail after adding a second interface," which often indicates the interface to subnet mapping is wrong. The best answer usually involves ensuring the vNIC is attached to the correct subnet and that routing intent matches interface purpose. The main lesson is that interface attachment is a first-order configuration, so mistakes have immediate and broad effect. Another pitfall is disabled source checks, enabling unintended routing behavior, because some environments use source and destination checking to prevent workloads from acting as routers. Source checks help ensure that a workload only sends and receives traffic that matches its own assigned addresses, which is a safety mechanism to prevent accidental or unauthorized forwarding. Disabling source checks can be necessary for legitimate network functions, like network appliances, but doing so on ordinary workloads can allow them to forward traffic, potentially bypassing intended gateways and segmentation controls. This can create shadow routing paths that confuse troubleshooting and weaken security, because traffic may flow through a workload that was never designed to be an enforcement point. In exam terms, scenarios that mention instances acting as routers or unexpected forwarding often relate to source check behavior, especially when virtual appliances are involved. The best answer typically preserves source checks for normal workloads and disables them only when the workload is explicitly intended to forward traffic as part of the architecture. This is a classic example of an option that solves one problem while creating another if applied indiscriminately. Operationally, tagging interfaces and documenting ownership helps because vNIC configurations are easy to change and easy to misinterpret, and clarity reduces the time to fix incidents. Tags can encode purpose, environment, and owner, making it easier to identify why an interface exists and which team is responsible for its policy and routing. Documentation helps prevent duplication, prevents drift, and supports troubleshooting when someone unfamiliar with the original design is on call. Ownership matters because interface-level policy often requires coordination between security and networking teams, and unclear ownership leads to slow fixes and finger-pointing. In hybrid environments, vNICs may connect to different routing domains and different trust zones, so the risk of misconfiguration increases as complexity grows. Exam scenarios sometimes hint at operational constraints, such as limited staff or frequent changes, and designs that include clear ownership and naming often align with the best answer because they reduce long-term risk. The broader lesson is that interfaces are not only technical objects, they are governance objects. A memory anchor that fits this topic is attach, address, allow, observe, then optimize later, because it matches how interface design becomes operational reality. Attach means the vNIC must be connected to the correct subnet and trust zone because attachment defines reachability boundaries. Address means the vNIC must have correct addressing and identity, including avoiding media access control duplication and ensuring routing intent aligns with interface purpose. Allow means security groups and stateful rules must be correct at the interface because that is where traffic is permitted or denied. Observe means you need logs and monitoring attached to the interface so you can detect misbehavior, performance bottlenecks, and unexpected flows. Optimize later reminds you that once correctness and visibility are established, you can tune performance settings like offload and queue depth to meet throughput needs. This anchor keeps you from tuning performance while the interface is still in the wrong subnet or governed by the wrong policy, which is a common troubleshooting mistake. To end the core with a design prompt, choose a vNIC layout for two trust zones, such as a management zone and an application zone, and justify the layout using clarity and blast radius thinking. A clean approach is to use separate vNICs for management and application traffic, each attached to a subnet that reflects the intended trust boundary and routing behavior. The management vNIC should live in a restricted subnet with tight security group rules, allowing only necessary administrative access from approved sources, while the application vNIC should live in a subnet designed for user-facing or service-facing flows, with rules aligned to the application's exposure needs. Routing should ensure that management traffic does not traverse the same paths as application traffic unless explicitly intended, reducing the chance that an application compromise becomes a management compromise. Observability should be configured so that traffic on each interface can be monitored separately, allowing faster detection of abnormal flows or unexpected bandwidth consumption. In exam terms, this design matches the principle of separating control plane and data plane, which is often what scenario prompts are asking for when they mention trust zones and blast radius. In the conclusion of episode 24, titled Network Virtual Interfaces, What vNICs Imply for Control and Visibility, the key point is that the vNIC is where workload identity, policy enforcement, and observability meet. Virtual interfaces attach workloads to subnets and routing domains, and multiple vNICs allow separation of management and data traffic, reducing blast radius and improving clarity. Media access control identity still matters, and duplicates can create confusing reachability problems, while subnets per vNIC help ensure purpose is clear and policies remain consistent. Security group rules often apply statefully at the interface, making correct attachment critical, and performance characteristics like offload and queue depth can influence throughput when workloads are under load. You avoid pitfalls like misassigned vNICs that break access immediately and disabled source checks that can enable unintended routing behavior that bypasses controls. You improve operations by tagging interfaces and documenting ownership, and you keep the anchor attach, address, allow, observe, then optimize later as your sequencing tool. Assign yourself one configuration, narration by taking a two-interface workload and describing, in order, which subnet each vNIC attaches to, which rules apply, which traffic uses which interface, and what logs you would review to confirm the design works as intended. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.